SwayamPrabha. Digital India. Educated India.
So, friends, in the subject on production and operations management, we are talking about facility design. There we first talked about the location of the facilities, then we discussed the layout of the facilities, and today we are going to talk about line balancing. As I said in the previous session, the facility layout is relevant for batch production system and job shop production system, whereas line balancing is important for flow lines and mass production systems. So, today we will see that what is the importance of this line balancing and the various types of techniques and algorithms available to do the line balancing, and then we will talk about some generic concepts also about line balancing. When we say flow line, there are two types of line we talk about. One is called fabrication line, second is called assembly line. In fabrication line, the workstations are basically machines, technology is there, whereas when we say assembly line, there the workstations are human resource. The difference, why we differentiate the two lines? In fabrication line, sometimes it is difficult to transfer the work from one workstation to another, whereas in assembly lines, where the human beings are, workers are the major resource, by giving the training, we can shift the workload from one workstation to another. Before doing that, let us understand why we are doing the line balancing. Let us say there are three workstation in the line. Workstation 1 has a workload of 10 minutes. Workstation 2 has a workload of 5 minutes and workstation 3 has a workload of 15 minutes. And if we see that what is going to be the output of this line, how many units per hour this line will be able to produce. This line will be able to produce because C is the bottleneck stage, which is having the highest cycle time, operation time. So, 4 units per hour we are able to produce. While producing 4 units per hour, this operation will be used 100% of the time, this will be used only 33% of the time and this will be used only 66% of the time. So, we are the utilization of the workstation A and B is very less, whereas C is fully utilized. There are two implications of this. One, your total resource utilization is less, and number two, there may be interpersonal relation difficulties. Worker C may feel that I am working more, I am working throughout the shift, whereas these worker A and B are working only partially. That also you can address by shifting these workers to some other assignments or giving some other activity, but obviously the utilization of workstation A and B is very less. So, what we can do as a line balancing, what we can do in this case is, somehow if we can shift the 5 units of work from this place to this place, if we are able to shift 5 units of work from workstation C to workstation B, then this workstation will have a work of 10 minutes, this workstation will also have a work of 10 minutes and this workstation will also have a 10 minutes. So, in that way line is totally balanced, all the 3 workstations are having the same workload and we will be able to produce 6 units per hour. So, without any addition of resources, our productivity will increase by 50%. You will find our productivity has increased by 50% just by balancing the load. But if these 3 machines are technology machines, if I take the example of from a machine shop, machine A is the lathe machine, machine B is the my milling machine and machine C is the grinding machine, then it may not be possible to shift the work from a grinding machine to a milling machine. So, this type of line is called a fabrication line. This is a fabrication line, machining line. So, it is not possible to shift the work from one workstation to another in fabrication line, but still we are having ways and means to balance this, we will study that. On the other hand, if this is a assembly line, and these are the 3 workers, then obviously very easily we can shift the work from workstation C to workstation B, if it is if these are the workers only, human beings only, and they can be trained for activities, and work can be easily transferred from workstation C to workstation B. This is there when we are assembling it. So, then it will called assembly line. So, I hope you will get the idea what is meant by assembly line and what is meant by fabrication line. In fabrication line, our workstations are mainly machines, and it is not possible, generally it is not possible to transfer the work from one workstation to another, whereas in the assembly line the stations are human beings. So, transfer of work is possible by providing the training. So, what to do if it is a fabrication line? Most of the algorithm in line balancing is related to assembly line, that is why this topic is also called assembly line balancing. But still, let us see if it is a manufacturing case and our workstations are machines, equipment, what we can do in case of a fabrication line, how to balance a fabrication line if it is imbalanced. What we can do, take the same example of 3 machines, just like we did in the previous case. A, B, C, this has a work of 10 minutes, this has a work of 5 minutes, this has a work of 15 minutes, and these are all machines. This is lathe machine, this is my milling machine, and this is grinding machine, grinders. Okay. So, what we can do now, suppose it is not possible to transfer the work content from C to B. I can duplicate the machines C. I can have 2 machines of C. In that case, by adding a small resource, my cycle time, if I am having 2 machines of C, the cycle time of this will reduce to 7.5, this will reduce to 5 minutes, and this is 10 minutes. So, earlier I was able to produce 4 units per hour. Now, by adding a small resource C, duplicating this, I will be able to produce 6 units per hour. So, this is in productivity, you might recollect when we said the productivity is equal to output by input, and we said that there are 4 ways of increasing the productivity. We said that increase in output for the same amount of input, for the same output reduction in the input, increasing the output as well as reducing the input, and fourth was a small increase in input and a substantial increase in output. So, by adding one machine, that means 1/3 of the resources, we are able to increase the productivity by 50%. By adding resources of 33%, we are able to increase the productivity by 50%. So, small increase in input and substantial increase in output. Here I have shown only 3 processes. If there are 20 processes and one is bottleneck, if you add that, you will find there are much more gains in the productivity by adding small input, and there is substantial increase in the output. So, one of the ways to increase the balance the line is by adding extra equipment. Another thing which we can do in this case is we can perform the work study. For work study, which one is the right candidate out of the 3 A, B and C, which one I should try to improve? Obviously, the bottleneck stage. If with the help of work study, I am able to reduce the time from 15 minutes to 14 minutes. By doing the work study, if I am able to reduce the time of this element, this workstation, the task time from 15 minutes to 40 minutes, that will directly improve my productivity. So, by doing the work study, I can reduce by providing some simplified tools, by providing some better training to the worker, or doing some setting of this machine, I can improve the or better loading unloading of the machine. I can reduce the cycle time from 15 minutes to 14 minutes, and that will increase my productivity without adding any additional resources. So, work study is another option. We identify the bottleneck stage and then we perform the work study there. We will see as one of the units on work study also, and then that will help us in improving the productivity and balancing of the line. Another is we can do some R&D also. We can do the process planning itself. We can do some process planning again. Maybe certain part of this grinding can be achieved or better tolerance can be better finish can be given at the lathe machine itself. So, that there is less grinding requirements. So, or maybe we are putting some better grinding wheel or increasing the speed of grinding, by which we can reduce the cycle time of the grinding process. So, by doing the R&D on this, one, reducing the work content at the grinding machine, second is speeding up the metal removal rate of the grinding process, and by which we can reduce the time taken at the grinding machine. So, that my line is balanced. Another important thing which we can do is, let me erase this. Sorry. Another important thing which we can do is by better maintenance. There may be a breakdown of these machines. Suppose all three machines are working, have a utilization or uptime, we call it uptime of this is 90%, this is also 90%, this is also 90%. If somehow if we are able to improve this uptime of this from 90 to 95%, then that will also help us in better production and increasing the production per day from the line, complete line. So, better maintenance can be done on the bottleneck stage, so that by which we can improve the performance. Another thing, with the help of work study also or independently also, we can plan for better tools, jigs and fixtures here. For C, we can think of better tooling, better jigs, better fixture, so that I can run the machine at a higher speed and at better material removal rate. Another important thing which is not listed here, we can put one inspection station here. So, that when the material is going to this place, there is less rejections at the C. We can reduce the rejection of C workstation C, that will also help us in having a better output from the complete line. If nothing, if we are not able to do anything in the bottleneck of the debottlenecking the critical stage, we can work in the differential shift. We can allow the shift machine 3 to work in 3 shifts per day. Let this work for 1 shift per day and let this work for 2 shifts per day. Okay. So, by doing that, all the 3 machines are going to be 100% utilized, and we can achieve the balancing also, and we can improve our production rate and reduce the cost per unit. But disadvantage of this method is differential shift is inventory is going to be built up. The inventory which you are going to build up in 1 shift, that is going to be consumed in next 2 shifts. So, you have to provide some kind of a storage space in between. We have to provide inventory storage space here in between. We have to provide some inventory storage space, and that is one of the disadvantage of differential shift. But in industry, this is very widely used practice of running the differential shifts if you are not able to balance the machines with the help of other technological interventions. So, this is about fabrication line, where more engineering solutions we have to found rather than the management related issues. It is more engineering interventions are required to balance the fabrication line. Now, coming to the assembly line, here each workstation carried out certain set of tasks, just like assembly of a pen. If I look at this pen which I am carrying, this pen has several components and parts. So, if there is an assembly operation of this pen, let us say this has 4 components. One is the barrel, second is the refill, third is the nozzle, and fourth is the cap. So, these are the 4 activities which are. So, first is, if I am doing the assembly of this pen, a simple example, I will pick the barrel, and then that is one element, pick the barrel from the table. Then second element is pick the refill and insert it in the barrel, that is the second task. Third task is placing the nozzle on the refill and tightening it. So, this is my element number 3, and element fourth is put the cap and tighten it, and fifth element is put it away. So, this is how this is a small example of assembling a pen. But if you look at the assembly of a fan, assembly of a car, this here we are having 5 elements. This number of elements may be few hundred or few thousands. In a real life scenario of even for small product like fan, there may be more than 100 such elements can be there, or in car it may be more than 1000 or few thousand such kind of elements are involved in the assembly of a car. So, each workstation carry out certain set of tasks. So, this task can be divided among various workstations. So, we have to make the set in such a manner that each set all the sets are equal to each other in terms of time content. So, each suppose I have to produce let us say 60 units per hour, that means each workstation will have a time of 60 seconds, 1 minute. If I have to produce 60 units per hour, each workstation will have a time of 1 minute 60 seconds. So, as far as possible I have to ensure that each workstation has a set of tasks, the total time of those tasks is equivalent to 60 seconds. That is the purpose of line balancing. So, we will see that how to do that. Then because since the conveyor is moving at a constant speed, so each workstation has same time to perform the work. As I said, if it is 1 minute is there, each worker will have 1 minute available. The set of tasks should be according to this time cycle. So, no workstation should have a time more than 1 minute, it has to be lesser than that. So, that is the concept of assembly line. We have to divide the total work content into various workstations. Purpose, now you must have understood why we are doing this assembly line balancing. Match the workload between assemblers, all the workstations should have the same amount of work content. Identify the operations bottleneck. By doing the assembly, by doing the line balancing, I will get to know that the workstation which is the bottleneck, and the output of the line depends upon the output of the bottleneck stage. As we have seen in the previous example, 3 workstation, workstation 1 has 10 minutes time, workstation 2 has 5 minutes and workstation 3 has 15 minutes. So, the output of the line depends upon the bottleneck stage, that is station C. So, with the help of line balancing I can identify which is the bottleneck stage and what is going to be my total production rate. And also I can determine with the help of this how many workstations are required for a particular production rate. Number of workstation will depends upon how many units per hour I want to produce. Then I can reduce the cost of production also with the help of better balancing. As we have seen that with the help of balancing, I can increase the production rate by 50% from 4 units per hour to 6 units per hour in a small example. So, my production, I can increase the production rate by balancing the line. Another important aspect is related to finding the standard time. Standard time is time required to produce 1 unit. So, by doing the balancing I get to know that time required to produce 1 unit is 15 minutes. Every 15 minutes I am going to get 1 unit. So, based on this I can plan my dispatching. If I am quoting for a tender or something to supply certain material, I can give realistic time schedules also, and I can arrange the dispatches, I can arrange the transportation system also according to that. So, that is these are some of the applications of assembly line balancing, very important requirement, because after doing all the fabrication, the last step in most of the manufacturing is assembly line, whether it is assembly of a fan, whether it is assembly of refrigerators, air conditioners or any product. At the end we are after manufacturing parts and components, we are assembling it. Just like we have seen the example of a pen also, after producing barrel with the help of molding, refill and other things, the last step in the manufacturing is assembly of the components. So, with the help of this assembly of the component, I get to know what is going to be my production rate, how many units per hour, per day, per shift I am going to produce, and based on this I can plan my dispatches, I can plan my I can give targets also to the production team, and I can also give commitment to my sales and distribution team. If we see that this particular subject, it started with Henry Ford, when first time he put at the Ford Motors the concept of assembly line. Prior to that you will be surprised, these days it is not happening. I have seen in 1990s when I visited in India one of the plant manufacturing tractors. It was not having a line concept, it was more like a fixed location layout. They were manufacturing tractors in a big hall, one tractor is manufactured at one place, another tractor is manufactured at another place. So, fixed location. So, 20 such teams are working on 20 different assembly of the tractor. So, that was the concept. In 1913, Henry Ford took the initiative, that is also called major revolution in industry, when he take the help of division of labor as propounded by the father of scientific management F. W. Taylor. F. W. Taylor gave the concept of division of labor. That means, total work required to perform a task, total labor required to perform a task, assembly of a complete fan, it need not be done by one person, it can be distributed, it can be divided among several workers. So, that is the concept of division of labor. The total labor required to perform a certain task, it may not be given to one worker, rather that total labor can be divided among various workers, various workstation. So, Henry Ford took the clue from that, and he divided the total assembly of a car among various workstation, among various workers, and that give birth to the assembly line manufacturing, assembly line concept. Then the first time this term was given in literature by Helgeson, and then first published paper is by Salvation. So, this line balancing in the literature in our academy books came from 1955 onward, and then various heuristics were developed in 60s and 70s, and now in when we talk about today, all softwares which are used in operations management, production planning and control, they are having inbuilt feature of line balancing, and it can be done in a very dynamic manner also. These heuristic which we are going to study today, they are more static in nature. When I say static, that means one time you give the data, one time solution they will provide, but if there is a change in the demand, if the demand is changing or the processes are improving or some dynamic manner, then these softwares are not able to perform, but these algorithms are not able to perform, but the softwares which are available, they are in a position to dynamically balance the line as per the requirement. Or we will talk about the multi-model also. If on the same line you are manufacturing different models of the car or different type of fans or different products, and where the different elements have different tasks, have different task time. So, as the product changes, the line balancing also changes, it is displayed, and the workers location also changes, conveyor speed also changed if there is a. So, there can be 2-3 situations when we talk about dynamic. It can be due to multi-model or mixed model. In mixed model, the components are manufactured in mixed manner. That means, first you are manufacturing model A, then you are manufacturing B, then C, and then maybe again B, again A, C, or in any manner you are manufacturing like this. So, conveyor is moving in this direction, or there may be 2 units of it. So, in some manner, so that is called mixed model. Whereas, in multi model you are producing in batches, you are producing one batch of A, let us say 20 units, then you change over and you produce B, let us say 15 units, then you produce the model C, let us say 25 units. So, this is called multi-model assembly line, and this one is called mixed model assembly line. So, in that case you need the dynamic balancing. Dynamic balancing is also required if there is a production rate is changing and you want to catch up, you do not want to build the inventory in a JIT environment, and if there is a change in the production rate. So, with the change in the production rate you have to rebalance the assembly line. So, these are some of the applications, and the present day softwares are in a position to handle this. They are some derivatives of these techniques which we are going to study. Let us see, before going to the methods of line balancing, some definitions. Task time, the time required to carry out a task, just like in case of pen, the time required to pick the barrel from the table and bringing to the right level. So, that is task time. Picking up the refill and inserting into the barrel. So, that is the second element, second task. So, that is called task time. So, total work required to assemble the product is divided into various tasks, and we, with the help of a work measurement time study, we find out the time required to carry out a particular task. So, in that way we are having a list of all the tasks, and we also know the time required to perform that task. Then workstation, workstation is a physical area where the work is performed. So, one workstation performs certain part of the total assembly, another workstation perform another part of the assembly, and like this. A total conveyor may have 20 workstation, may 30 workstation. In car manufacturing, the total line may have more than 70, 80 workstations also. Then there is a station time. We have given certain tasks to the station, and the summation of all these tasks is called station time. We show it with Sk, where I is equal to 1 to k. The k tasks are given to workstation k. So, the total time of all these task times is called station time. And then the sum of all these tasks which are there, the sum of all these tasks is called total assembly time. With the help of when I am taking the next some example, you will get to know with more clarity. So, that is called total assembly time, the time, total time of all the tasks, or it can be total time of all the workstations, because all the tasks are going to be assigned to different workstations. So, I can take total assembly time as equivalent to the time of all the tasks, which is also equal to time of all the workstations. Then there is an important parameter, that is production rate. We have to balance the line for a particular production rate. Suppose if the production rate is 10 units per hour, then it is coming, then each workstation should not have time more than 6 minutes. Each workstation will get a time of 6 minutes, which is called cycle time, the time interval between parts coming off the production line, or cycle time is equal to 1 by production rate. So, if P is equal to 10 units per hour, cycle time is 1 by P is equal to 1 by 10 hours. This is equal to 60 by 10 minutes. Okay. So, this is how there is a relationship between production rate, cycle time, and these are two are connected. In a given situation, you may be given a production rate, that you have to balance the line for a given production rate, or you have to balance the line for a given cycle time. Okay. So, then obviously, it is not possible to completely balance the line, that all the workstation are having exactly equal timing. So, we will calculate the efficiency of this line and also the balance delay. How much is the balance delay, the gap between the ideal situation and the achieved situation. So, let us first see the line efficiency. Line efficiency is equal to, here n is the total number of workstations, and C is equal to cycle time. So, the total time is equal to n into C. The total time put in to produce the product is n into C, and during out of n and C, T is the total work achieved. So, the line efficiency T by N C, and 1 minus T by N C is the delays, which otherwise also we can say what is the total ideal time, n into C is the total time taken, out of that T is the productive time. So, N C minus T is the ideal time divided by the total time taken. So, that gives the balance delay, total ideal time divided by total time a product spent in the line. So, that gives the balance delay. So, we will see after doing the balancing, we will see what is the line efficiency and what is the balance delay, and that will tell us how good is our line, whether it is balanced or it is not balanced. So, based on that we will get to know. So, our objective here is to minimize the balance delay. Our objective here is to minimize the balance delay, and two more constraints are there in this. The total station time, as I said, like in the previous slide, we said that total cycle time is, let us say, 6 minutes. So, I cannot assign time work content more than 6 minutes to any workstation. So, the time total content given to any workstation should be less than or equal to the cycle time. I cannot give more than 6 minutes of task to any of the workstation. Second is, my cycle time cannot be lesser than the maximum task time, otherwise that task will not be performed. Suppose one of the tasks require let us say 7 minutes, one of the tasks requires 7 minutes, and you are saying cycle time of 6 minutes. How a worker is going to perform a task of 7 minutes if you are assigning only 6 minutes to a particular workstation. So, we have to keep that T I max should be lesser than or equal to cycle time, or other way say we say C should be greater than or equal to T I. I cannot keep a cycle time lesser than the highest elemental time. So, these two things we have to keep in mind. Now, taking clue from this formula, if I have to minimize the D, for minimizing the D I have to minimize n into C, because T is constant, 1 is constant. So, therefore, to improve the line efficiency we have to reduce n into C, and n into C can be reduced in three ways. One is keeping n constant and reduce the number of workstations. Keep the n constant, let us say 5 workstation, and if I can reduce the cycle time for 6 minutes to 5.8 minutes. So, that is one way. Second is keeping the cycle time same, reduce the number of workstations. Third is reducing both of them. So, we will see algorithm, most of the algorithms are for a particular cycle time reduce the number of workstation. How I can produce a particular production rate with the minimum number of workstations. But later on, once we have done that, we can further look at that. We will see in one of the examples that we can further look at that, and we can achieve that also. Further, we can reduce the cycle time for the same number of workstation. We will see with the help of the same example. So, our total objective here is how to reduce the number of workstation to achieve a particular production rate. Now, coming to the procedure part of it. Now, by now you must have understood what is going to be the procedure. Divide the work into various work elements, tasks, and the smallest unit of work that can be performed independently. Like I said, picking the barrel from the table to the hand, that is a work task which can be performed independently, and it cannot be broken further to another small level. So, that is why this is the task which can be performed independently, and second, this is the smallest unit of work which can be performed independently. Second is obtained the standard time for each task. Then with the help of time study, we find out the time required for each of these tasks. Then we also need the predecessors also. I cannot put the cap on the pen unless I put the refill and the nozzle. So, cap can be put only when nozzle has been inserted, and nozzle can be put only once the lead once the refill has been inserted. So, this is called predecessor or precedence relationship. So, that also I need to have. I will show you with the help of one example what is meant by precedence diagram. I have to prepare the precedence diagram also, or I can give this information in the tabular form also. We are having several techniques. I have listed only 5 here, which I am going to discuss here, but there may be another 10-15 more techniques or even more techniques are available. But to understand the basic concepts and various concepts behind that, we will discuss these 5 techniques here in this session. These are largest candidate rule, Kilbridge and Wester method, ranked positional weight technique, Moody and Young two-phase heuristic, and COMSOL. COMSOL is computer method for sequencing operations for assembly line. These are the some more formulas which are going to use here. The cycle time is equal to available time divided by desired production. As I said, if desired production rate is 10 units per hour, then my cycle time will be available time 1 hour, then this will be actual cycle time will be 6 minutes like this, and minimum number of workstation required is the sum of all task time total T divided by cycle time. Suppose the total assembly time required is let us say 85 minutes, and each workstation has we are assigning 6 minutes of task. So, I require 14 point something. So, 15 workstations are minimum 15 workstations are required to perform this task. So, minimum 15 workstations are required to perform this task. So, from there we will get an idea that how much minimum number of workstations are required. In actual, because of imbalancing, you may require 15 workstation, or it may be 16 or 17 also, depending upon the situation. Then average resource utilization, we have already said, efficiency of the line, sum of all tasks divided by number of workstation into cycle time. We are going to use that to assess the performance. Now, take one example, and before that let me show you the example, then I will come to the previous slide to tell you. So, this is the kind of example we can have. The company has to produce 300 computers per day, and expected line is operating 420 minutes per day. So, this is the kind of data we are having. So, one, I know that what is going to be my production rate in a shift of in a day of 420 minutes, I need 300 computers. Then it require 14 different tasks, 1, 2, 3, 14 different tasks which has been given code of A to N, and then I have the information about the task time also, and then I am having information about their immediate predecessor also, which is the active. I cannot perform B unless A is carried out. This indicates that these 3 activities can be performed only after A has been carried out. Similarly, E and F can be carried out, there is no constraint for that, there is no predecessor for that, and like this I will help further explain on this. 3 techniques I am explaining here, and we will start with the ranked positional weight. First technique is largest candidate rule. In this technique, we list all the elements in the descending order of Ti. That means, element which is having the highest task time, that is put at the top, and the element which is having the least time is at the bottom. So, the priority is to assign first the element which is having the higher time, which is having the largest time element. Then assign element to the workstation without breaking the precedence relationship. In any case, we cannot break the precedence relationship. I cannot do something unless some other activity has been carried out, which need to be done. There is another method which is called Kilbridge and Wester method. In this method, the tasks are assigned to the workstation according to their position. That means, how many followers they are having. The task which is having more number of followers is scheduled first, and the task which is having less number of followers is scheduled later on. So, that is the kind of algorithm this is having. So, in this method, tasks are assigned to the workstation according to their position in the precedence diagram. So, we determine the number of followers of each task, list all the elements in the descending order of number of followers, assign element to the workstation without breaking the precedence relationship. The third technique, which is very popular, which combines the best part of these 2 techniques. So, RWA combines the largest candidate rule as well as the Kilbridge and Wester method, and it takes into account both the task time and the followers. So, we calculate the ranked positional weight of each of the tasks, which is a combination of the task time of that particular task plus all the time of all the tasks which are following that particular task. And then we list the elements in the descending order of RPW, and we start assigning them starting from largest to the smaller RPW element. So, that way we will discuss these 3 techniques, starting with ranked positional weight technique, and we will take one example to explain all the 3 techniques. So, in this example we are having a assembly line which assembles the computers, and we have to produce 420 in 420 minutes we have to produce 300 computers per day, and this is the data available to us, the various tasks which are need to be performed, the task time and immediate precedence is also given. So, I am again written the same question again. So, here the production rate requirement is 300 computers per day, and operating minutes is 420 minutes per day is available. So, the maximum cycle time is equal to 420 minutes is available, and we have to produce 300 computers. So, the maximum time available is 14 minutes. So, the maximum time available to manufacture one computer is 14 minutes, and how many minimum number of workstations required? For that we have to make a total of total time. So, these are nothing but TIs. the task time of A, B, C, D, and if we see this, if you sum up all the timing together, summation of this is equal to 551. We can do that, we can total this 55 plus 30 plus 50 plus 42 plus 20 plus 25 45 so on and up to 40. If we make a total of this, the total time is 551. So, 551 is the total work content, that is capital T, and we are having a cycle time of C. So, how many minimum number of workstations required? Minimum number of workstation required is 551 by 14, and this number is equivalent to we can do that. So, the total time required to assemble the computer is 551, which is the sum of all these elements. Now, I have reproduced this question here again. Now, let us do some calculations here. The production rate requirement is 300 computers per day. The time available per day is 420 minutes. So, the maximum cycle time which is available is 420 minutes divided by 300 computers per day, and 420 minutes per day is available. So, the time available per computer is minutes per computer, and this is equal to 84 seconds. 1.4 into 60, 84 seconds are available to produce one unit. And we have seen that 551 is the total cycle time, T is equal to 551, and I can give maximum 84 seconds to one workstation, 84. So, this is the minimum theoretical minimum number of workstation required. In actual, it will be more than this. This will be 6.55, which is equivalent to 7 workstation minimum is required to assemble these computers at a production rate of 300 computers per day. So, this is the first starting point we have to find out. Now, I am going to balance the line with the cycle time of 84 seconds, and using first we will use the ranked positional weight technique to balance this line for a cycle time of 84 seconds. And I know that minimum 7 workstations are going to be used to assemble the computers at a production rate of 300 computers per day. So, I have reproduced the data just to explain the procedure part. So, the same data which was there in the previous slide, I have copied it here. So, first task is to draw the precedence diagram. Let us draw the first precedence diagram. We write the elements which are not having any predecessor. So, I will write A, I will write E, and I will write F. Then I will write elements tasks which are following A. So, B, C and D, these are the 3 tasks which are following A. So, I will write B, I will write C, I will write D. So, these are the 3 tasks which are carried out after A. There is another task also which is carried out after A, that is task G. But task G also required to be carried out only once E and F have been done. So, I can do G only once A, E and F has been done. So, like this I can draw the diagram here. So, I can do B only after doing A, I can do D only after doing A, I can do G once A, E and F has been carried out. Now, let us see what happens to I. There is a element H. Now, the next is we have done this. Now, next is the element H. H can be done once B, C, D and G are carried out. So, I will write H here and I will connect them to H. So, I will do H only when these have been done. Now, once H is done, I can take I can take J and I can take K, I can take K also, because I, J, K are following task H. Once that is done, then I can do J after L, I can do L after J. So, this is L. I can do M. I can do M after J. Sorry, I can do K after H. We have done that. Now, let us see L. L after J we can do L, and we can do also M also after this. And then there is a N which is to be carried out once these has been done and this has been done. So, I can draw this little bit here I and connect it here. You may require 1 or 2 iterations to nicely draw this diagram. So, this is my precedence diagram. On this I can also write the timings also. On this I can write A require 55 seconds, B requires 30, C require 50, D require 42, and then E requires 20, this requires 25, G require 45, H requires 60, I require 36, J needs 42, K needs 30, L needs 40, M needs 36, and then N is 40. So, like this. So, this is the precedence diagram. First step in the RPW technique is to draw the precedence diagram. So, which we have done now. Once we have done that, now we will calculate the ranked positional weight of each of these elements. We will calculate the ranked positional weight of this. The formula for ranked positional weight is RPW of element A is equal to time of element A plus summation of all the tasks, timing of all the tasks that follows A. So, here so I have to take T A plus what are the tasks which are following A except E and F. If you find here except E and F, all other tasks are following, it is not immediate follower, all the followers. So, it will be T B plus T C plus T D plus T G plus T H plus T I plus T J plus T K plus T L plus T M plus T N. So, these are the total RPW of A. So, which we can calculate by summing 55 plus 30 plus 50 plus 42 plus 45 60 and so on, or other way around I can do is 551 is the total time. Out of that, if I make a minus of 20, I can take other way around also 551 minus 20 plus 25. So, that gives me a number which is 506. So, 560 is the RPW of element A. Similarly, if I have to calculate the RPW of let us say element I, RPW of element I, that is equal to T I plus I is followed by N, T N. So, that is equivalent to 36 plus 40 is equal to 76. If I have to calculate RPW of N, that is T N, and there is no task which is following it. So, then this is equivalent to 40 only. So, I hope you got the idea how to calculate the RPW. It is a very simple relationship. RPW is equal to the elemental time of that task plus the total of all the tasks which are following that task A. So, with the help of this we will calculate the RPW of each of these elements, and I have reproduced this in this particular table. Element A has a RPW of 506, element B 314, element C 334 like this, or if you see we calculated for N it is 40, for M I can very easily 40 plus 36 76, for L it is 40 plus 40 80, for K I can do that 40 plus 30 70, for J let us see J. What is going to, how I get this J 158? J means 42 plus all these elements 36 plus 40 plus 36 plus 30 plus 40. If we sum this, we will get 158. So, like this you can work from the backward also from the last element, then it is easy, keep on adding 1 by 1 and we can calculate the RPW of element j like this. So, it is very easy to calculate that. So, once we have calculated the RPW as the procedure says, now arrange the elements in the descending order of RPW. So, that element which is having the highest RPW is kept at the top and element which is having the least RPW is kept at the bottom. So, we have arranged them in the descending order of RPW. Now, let us move forward. Now, once we have done that, now we will assign them to the workstations. So, I have reproduced the previous slide table, where we have find out the RPW of each of the tasks and arrange them in the descending order. Now, we will do the allocation here. So, we will open the workstation number 1 and our cycle time here is 84 seconds. The cycle time is 84 seconds. So, when no task is assigned, the time available is 84 seconds. Now, we will find out the elements which are not having any predecessor. The element which are not having any predecessor, there are 3 elements which are not having any predecessor. So, they are the feasible tasks which can be assigned here. These are not feasible tasks. This group of tasks are not feasible at this stage to be assigned, because they depend upon something else should be carried out before these tasks can be done. So, we are having A, F and E. Out of that we will find out the one which is having the highest RPW. So, element A is having the highest RPW. Then we will see its cycle time, its task time, whether task time of A is less than the time available. So, 3-way test is there. One, I have to find out the element which is not having any predecessor. Then out of that select the one which is having the highest RPW, and third, see that the element time of this is lesser than the time available. So, the T A is in our case is 55, which is less than 84. That means, task A can be assigned to workstation 1. Once the task A is assigned to workstation 1, the remaining time will be 84 minus 55 is equal to 20, this is 29 second. So, then I will say that 29 is available here and I will eliminate. So, 29 seconds is available now with the workstation number 1. Now, A is allocated. So, I will delete it from this list. I will also delete from the predecessor diagram wherever A is appearing, because now A is no longer a constraint. Now, which are the elements which are feasible? The elements which are feasible for the second round. Now, the feasible elements are A is already assigned, sorry. Physical elements are now F, E, C is now also open to be allocated, D is also open to be allocated and B is also open to be allocated. Out of this, now we will see that which one is having the highest RPW, that is F is having the RPW, and the timing of F is 25, which is less than 29. So, F can also be assigned here and the remaining time available is now 4 seconds. Now, there is no element which is lesser than 4 seconds, that means, I cannot assign any other element to this. Now, I will open the workstation number 2. Now, I will open the workstation number 2 and I will repeat the same steps for workstation number 2 also. Let us do that also, one step of this, then I will. So, time available for workstation number 2 is 84 seconds and after assigning F, I will delete F also from this list. Now, feasible elements are F is assigned E, C, D and B. These are the 4 elements which are available, which can be assigned. Out of that, the highest RPW is for E, that is 349. This is also assigned. So, E, I will assign E here. The time of E is 20 seconds. Once this is assigned, the time available is 64 seconds. Then I will take 64 here, E is assigned. So, I will delete E also from this list. So, now I am having available element, E is reduced and G is added here to the list, and C is having the highest RPW and it has a time of 50. So, I will allocate C here and 64 minus 50, 14 seconds are available here. So, like this, now there is no element which is lesser than 14, I will open the workstation number 3. So, in this case I will allocate the task to the various workstations. Let us see this which has been done here. So, workstation number 1 has a element A, then F, workstation 2 has element E, then it has a C, then workstation 3 we can do in the same manner. Okay. And with while doing this, so we are able to allocate all the 14 elements on 8 workstation. Now, remember our minimum number of workstation were 7, but it is not possible to assign all the tasks to this 7 workstation. We need 8 workstation to assign all the tasks. So, with this we can calculate the line efficiency, which is equivalent to T divided by N into C. So, T we already knowing it 551, cycle 8 workstations are required and each workstation has a cycle time of 84. So, I will get a efficiency of 82%. So, this is how we can perform the line balancing by using the RPW technique. So, it is a very useful technique and many softwares are using this particular algorithm, because it has the best of the both the algorithm, whether it is a largest element time method or largest task time method, or it is a Kilbridge and Wester method. And so, it take care of the number of followers also, as well as the time required for a particular element also. Both the aspects has been combined together in this case to allocate the task to this. I hope you have understood the allocation. Some practice is required. Practice is required to develop the predecessor diagram, precedence diagram with the help of table available. Second practice is required to perform the allocation of tasks to the workstations. So, these two aspects are important to be understood clearly, and based on that you can develop your own software on application also in this, or you can take a small project also. By visiting some industry, you can collect the data about the assembly operation going on there, and then you can fit in that data and find out the element time and the predecessors of that, and then you can perform the line balancing activity here. So, this is about the RPW technique. We will continue this session by understanding the 2 more methods, that is largest element time method as well as Kilbridge and Wester method. We will study 2 more techniques, one is Moody and Young method and the COMSOL also, and then we will discuss some miscellaneous aspects of line balancing. Thank you.